Hello everyone, I'm back after some break. I've got a lot of questions to answer. I have been asked a lot of questions, so I will start making short videos on those questions and will try to cover all of them as I move on. If I miss something, then please do comment below or below any other interesting video of mine, and I will try to get back with a tutorial video or an answer to you. Also, I am kind of struggling with my computer, so if you really want to support this channel, then please do consider donating some stuff when you are downloading the files from my website, and this will be all the money will be used to upgrade my computer, which currently is struggling, and it's been with me for like over 5 years now. So let's move on to today's problem. One of the subscriber has asked if I can make a short video on how to apply blast loading on structures. So instead of having everything ready, I will just define a problem because no problem definition was given to me. And this will also explain to you thought process, just making a tutorial. So there is no blast loading given to me. So I'm going to search for a random blast loading. So what I'm going to do now, I'm going to go on to Google and I will ask, okay, blast loading on structure. So when I search for it, one of the articles which comes through is on ResearchGate, which is called blast loading on structures. So I'm going to go through it and see if I can find something more relevant to my problem. So they give you some blast loading equations based on broad. This is one of the references they have given. They have also given another equation or model for blast loading. And this is given by this, where PS is the pressure, and which is the static peak, static wavefront overpressure in bars. These are the scale distances you see, and R is the distance from the center of the spherical charge, and W is the charge mass expressed in kilograms of the TNT. Again, many different types of curves are available depending on the type of detonator you are using, or depending on the type of explosion which is happening. And in this case, the function looks something like this, that the pressure goes up to peak in a very short amount of time, and then it dissipates and goes to this kind of problem, and everything, and the time scale in this case is in milliseconds in most of the cases. So I will see if I have to use that relationship or if I can really kind of get some kind of curve directly from this equation. They have given some curves here. We can go with that if you want to. So again, there is some different patterns they have given for different types of loads and structures. It depends on how far you are as well from the explosion center. So I think the best option is if I go, let's say, with this kind of function where I don't know what is the value of PS. PS is basically given by any of these equations, I think. And then PT is the pressure, how it varies with time, and so on. So I think this will be more time consuming if I start plotting this in Excel. So let me bring Excel up. And I will kind of generate a similar sort of curve with my case. So what I need is basically time and the pressure, which is overpressure due to the explosion on my structure. And again, this will be, let's say I'm going to go with, you can go with bar or you can go with pascals. So I'm going to go with pascals in this case, which is Newton per meter square. So you can just convert it directly. So in reality, when you go and look at this paper, then you can see you have to define all these variables, and then you can just define P as a function of time if you have already computed PS from this relationship or some other relationships which are given later on in this paper. So what I'm going to do for the current case, I will just assume a linear function, and I will say, let's say a pressure of 1 at a time 0, everything is 0. Then at a very small amount of time, let's say 1 millisecond or so, or let's say 0.5 millisecond. This means 0.5 exponent minus 3, which is a 5 exponent minus 4. The pressure goes up to, let's say 175,000 or something. And then it comes back to 0 at, let's say 0.2 milliseconds. Or 2 milliseconds. So in this case, 2 exponent minus 3. And in that case, the pressure goes there. So this means our pressure curve would look something like a linear increase. So if I plot this, then what you will see is here, and if I plot it as a line, as a straight line, then it goes to a maximum value and then it goes sharply to back to 0. If as you remember, there could be many stages, and it can also go in this way where you way as well with a non-linear function. In this case, we are keep our life simple to apply this. So everything is in my millisecond, so we need to model everything in ABAQUS in millisecond. So this is kind of an amplitude function. I already have videos on how to define amplitude in ABAQUS CAE, so you can look at those videos, but I will do it again from scratch in this case. So next thing is I need to sort out what sort of structure I'm going to use. So I will come back to this later on. Let me first think of a structure. So let's create a part. We create a 3D deformable, and let's go with a shell and extrusion. So what I'm going to do is I'm going to create a kind of a corrugation. Again, everything is just arbitrary. I'm just playing with my things here, and then I can extrude it. And let's say if I give a depth of 20 millimeter and see how it looks like. I think this is pretty small, so maybe I need to make it bigger. So I go back to part, and then I will extrude this, edit, and I can make it, let's say 200 and see what happens. So I think this is pretty long. Let's make it 100. Yeah, I think this will be okay for the time being. So this is it. I don't know if you're familiar with that. I teach a lot of oil and gas related courses. So you see a corrugated blast walls in many floating point offshore structures and also ships, which they use to transport oil and gas stuff offshore. And this blast wall is there to separate the dangerous stuff with the non-dangerous stuff. So it's for safety. So if blast happens, this is the first line of defense to keep the structure or stuff safe on the other side of the blast wall. So this is one of the corrugation. You will have a lot of corrugation in the actual blast wall. Now what I have to do, I have to define the properties in the property modules. So I will just go make my life simple. I will keep it elastic, and I will use, let's say, steel wall. So remember, we have the units of pressures and everything in Pascal, so we need to make everything in its meters. So this should be in gigapascal. So 210, and then we have to have 9 zeros, 3, 6, 9, and I use a Poisson's ratio of 0.33, which is typical of steel. Once I have done that, I will create a section, pressing this button, create shell, homogeneous material, I'm assuming it to be, and then I have to give a wall thickness of this material, this corrugation. So let's give a wall thickness of 0.002, which is approximately 2 millimeters. And material 1 is the material properties which we have just defined. It's going to use 5 integration points. Again, you can use more if you are not, if you're confused about this, then again let me know and I will try to answer your question on this. Then I will assign this section to the whole of the geometry here, and color is green, so material properties are assigned. Next I go to assembly module, and I will just bring the part here, instance part, and now I'm gonna go to step, create step. I'm gonna use a static general because my wall is fixed in this case, so I'm gonna use that. It could have a large deformation, so I'm gonna keep the non-linear geometric option to be on, and I'm going to use a large number of increment to be on the safe side. If you remember, if you use a smaller number and if the simulation requires more than those number of increments, ABAQUS will stop the job because this is the maximum number of increments you have allowed it to go up to. And I'm going to use a very small time increment because our loading cycle, if you remember, is from 0 to 2 exponent minus 3 seconds. So 2 exponent minus 3 means we need to start with 1 0 0 0 1, I would say. So it will have 1 exponent minus 5, and then similarly here also you can go up to 0.00001, 1 exponent minus 5 as the maximum as well. I will leave everything for the default as default, and now I go to interaction, but there is no interaction here, so I'm gonna skip that part. And now is the time where I will start to fix everything, apply boundary conditions and loading. So for this case, again, depending on your blast wall connections or connectors, which are on the both ends of the blast wall in general, so your boundary conditions will depend on this. For this case, and for simplicity, I'm gonna keep them fixed in all directions. I'm going to select these edges and also these edges. And the one of the edges is missing, so I'm gonna just try to rotate. And now keep pressing the shift button, and I can select the multiple settings. And now I'm gonna say, please fix all the degrees of freedom in all directions. So now everything is done. I'm gonna rotate it because I'm gonna apply a pressure loading from this side. And now I'm gonna go to the loads, pressure, continuous. And since I already have, I'll just rotate slightly so I can see all the faces. And so since I have all the values, so I will just select all the surfaces where I'm applying the pressure. So this whole thing is exposed to this pressure. And now it's asking which surface you want, because it's a shell structure, so you can apply it from this side or from the other side. So purple side is the other one. I want to apply from brown side, so I'm going to select brown. And now I'm going to give a magnitude. So I'm going to give a magnitude of 1 because I'm giving the actual values of the pressure in the amplitude function. And then I will say I'm going to create an amplitude function using table. I'm going to go back to my Excel sheet, copy this, and then time and amplitude, I'm going to give this. So now you have to make sure that these are the actual values, because you're using this value to be 1. So depending on the time increment, let's say if you are at a time increment of 0.001, then this times 0.001 times this will give you the value. So if it is maximum is 1, so maximum it can go up to is this. If you have used a value of 2 here, then the maximum will be 2 times these values at different time increments. So I hope this makes sense. I'm going to select this amplitude here. And now you can see the pressure is applied normal to all the surfaces here. I think it's a too large a pressure for the structure, but just for the testing, let it go like this. Now we go to the mesh module and we will make mesh. So again, making our life simple, or keep our life simple, I will try with a coarse mesh. Maybe this is too coarse, so let's use a size of this, and then mesh. Let's go with this mesh for the time being, and make sure you have selected the right type of element. So standard, linear, reduce integration elements, and these are shell. And I think this should work. If we get any error, we come back and we will sort it out later. So now we go to the job, and then we will create a simple job here. And that job is basically b-wall fake blast loading, because we just created a fake loading, but you can replace it with anything you really want. So I'm going to go with a full precision here. Always I do that. And then I'll just submit. Now I have submitted the job. So you can see my system is struggling, although number of elements are only 950. And if I now look at monitor the solution, how it's progressing, so you see it has submitted the job. It is now processing the input parameters, which are fine, and now it has started running the job. And you see the time increment required is less than the minimum increment. This means the load is very high and it is struggling to really do anything with it. So what we can do, we can go back and we can either change the material properties, or we can reduce the loading which we have, or we can basically change the thickness of the shell, because the thickness is too small. It cannot take that kind of load which is there. So I would suggest let's go with the loading. I would go with the loading thing, and I might go with the amplitude, because in the amplitude I have the actual value of the loading. So I will just use, let's say for the timing, to just for the demonstration purpose, I use a very small load, 175 Pascal or so. Now if I go back again, submit, monitor, again there are some problems. So you see there is system matrix has 528 negative eigenvalue, so this means the properties you have assigned might not be properly working. So let's go back and see firstly the element type it has used. And in this case, everything seems to be fine. Let's go to the properties and then section here. This is fine, so this one, and we can increase the thickness from 0.2 millimeters, so let's say 25 millimeters. Okay, and let's go back again, job, submit. So it looks stable now. You see the thickness was really small and it was struggling because of that. As soon as we increase the thickness of the thing, it basically started working properly, and you can see it's going fine now, and it has to go up to, but I think we can stop it here. I think I didn't define the total step time correctly. See, getting old now, so this total time should have been the same as what we have here, which is 2 exponent minus 3, right? So it should be 002. So by that time blast has completely disappeared, but in this case we keep it running. We let it run until 0.002, and then I will kill the job for the time for this problem to save some time. And as soon as it goes to 0.002, which is this, I'm gonna kill it, because I think we only need it up to that point. And this is kill now. So once this is done, I go to the results and just rotate it, because to give a kind of a physical sense of how it looks like. And now you can see this is how it looks like. So the stresses are much more higher because of the supports boundary conditions. And if you want to plot the displacement to see the maximum deflection, so this deflection is very much high in these areas. So again, we haven't used any symmetric boundary conditions on these edges. As I told you, these corrugations are repeated throughout, so we need to use symmetric boundary conditions here. And once you have defined those correctly, you will get the maximum deflection in this middle part. So let's quickly do that and see if I am correct or not. So let's do create boundary condition. We select symmetry and we select this is, I think, x direction, so x symmetric. Similarly, create symmetry, and this should be x symmetric as well. And now, so this structure cannot move in this direction, so you will have the other way around. And since the whole thing has a total time of 0.002 seconds, so this time it should terminate at that time when the blast has completely vanished. So see, now it has completed because I gave a total time of 0.002, which was the time when your pressure wave goes to 0 or explosion completely vanishes. So results, this, and you see that you have a completely different sort of distribution now. Again, most of the stresses are at the supports. And if I now plot the deflection, then you see your deflection is at the middle, which is more correct in my opinion. And especially if you plot U2, then that should be the maximum at this point. And again, there are, if you're designing the blast wall, then you have to look at different types of code like ABAQUS codes, and they give you analytical relationships to compute this value as well. So you can compare your FE analysis directly with those as well based on your elastic solution. And also if you define the elastic plastic properties, then you can compare the deflections here with your elastic analytical solutions given in the design codes. So I hope this made sense, and you will not only learn about how to define a blast loading, but you can basically define any type of loading on your structure and how to post-process the data. Also how to define material properties, loadings, and boundary condition in this tutorial. So I will see you with more questions and answers later on. And if you please support this channel, subscribe and like the videos, and keep viewing my videos so that I get some positive benefits or motivation out of my tutorials. Thank you very much, and bye for now.